All right, so we're going to find the volume obtained by rotating the graphs of f of x equals 9 minus x squared and y equals 12 about the line y equals 12, and we're going to do it for the interval between 0 and 3. Okay, so let me just go ahead and draw a graph so we can see what this is going to look like. Now, the function 9 minus x squared is just going to be the negative x squared function translated up 9 units, right? So it's going to cross the y-axis at 9, and I better make this a little taller. It's going to be important. So it's going to cross the y-axis at 9, and it's going to be a negative x squared function, so it's just going to go down. And then my other line that I'm using here in this problem is the line y equals 12. Right, so y equals 12 is just a straight line where your y value is 12 all the way across. And then we're just concerned with the space from 0 to 3. So from 0 to 3. And this thing's actually going to cross the x-axis at 3, because if you plug x equals 3 into the function f of x is equal to 9 minus x squared, you would get 0. So this point right here at 3, 0 is the end. Now, what's funny about this one compared to the other ones is that our axis of rotation is actually up here. Okay, it's not the x-axis. And so our shape is actually going to be this area from 0 to 3 of this curve to the line y equals 12. Okay, so we still will be able to use a disk method, primarily because this area right here is right next to the axis of rotation the entire time, right? So we're going to be able to use a disk method, but the one thing that's going to change here is going to be our radius. Okay, so I just want to talk about the radius. You know, if we rotated this area around, I just want to talk about what the radius would be right now, because we know, you know, the disk method is the integral of, you know, pi times the integral from a to b of our radius squared, and in this case we're going to do it with respect to x because we have a horizontal axis of rotation, right? But the radius is going to look a little different here. In times past, you know, when we were rotating it around the x-axis, the radius was just the function. But now our radius, which is always the distance from the curve to your axis of rotation, is going to change. So let me make this dark. This little black space right here is actually what we're looking for. Okay. So if you notice, the function gives us from the x-axis to the curve. So the function would give us that blue line right there. We actually want the black line right there. Well, the way we can get the distance of that black line is to take the fact that this line right here, the axis of rotation, is always at 12, right? And so if we wanted this black piece right here, you can see if we took the green piece, which is the large piece, and subtract out the blue piece, then what will be left over is the black, which is what we actually want. So what I'm going to do to get the radius of this one is I'm going to take the height of that green line, which we know is always 12, because we're dealing with the line y equals 12, and then I'm going to subtract the function, which will give us the height of the blue line. And the function in this case is 9 minus x squared. And that will leave us with the black line, which is what we actually want for our radius. So our radius will be 12 minus 9 plus x squared. If I just distribute this negative right here, okay, so minus 9 plus x squared. And so the radius will be equal to 12 minus 9 is 3 plus x squared. So when I go to my formula here for the disk method, I'll get the integral. And we were told in this problem to go from 0 to 3 of my radius, which is 3 plus x squared, all squared. There's my radius squared, dx, and then don't forget to multiply by the pi. So there's the setup for that one, which is the difficult part. And from there you can solve it using a calculator. Okay. Now here's the exact same problem, but with one small twist. Okay, so we're looking at the exact same problem, but I'm just going to change one little thing in this problem. So we have, 9 minus x squared that's going to go down. And then we have the line y is equal to 12. Okay, and we're talking about the area from 0 to 3. So here's my area here. But the only thing I've changed this time is that we're going to rotate it about the line y equals 15. So, up here at 15, I'm going to have a line. And now this is my axis of rotation. Right? So my axis of rotation is the line y equals 15. And so hopefully you can see that since there is a gap between my shape and my axis of rotation, I'm actually going to have to use a washer method in this case. Okay? And remember, the washer method tells us that we need the integral, pi times the integral from a to b of our large radius squared minus our small radius squared, and this one will be with respect to x since we have a horizontal axis of rotation again. Okay, so what I'm going to do now is just try to figure out what my large radius is, and then I want to figure out what my small radius is. I just need to figure out what these two radii are going to be, and then we can plug them in. Well, remember, the large radius is just whichever one is farthest from the axis of rotation. So, if I go from here to there, that's the farthest one from the axis of rotation is this black line right here. And so I'm looking for that distance right there. Well, much like I did with the last problem, the distance from the x-axis to my axis of rotation is just always 15, right? It's always 15. And the distance from the x-axis to the curve is always whatever the function is. So you can see here again, if I want to get this black line, which is the distance from my axis of rotation to my farthest curve, so it's my large radius, it would just be the 15, which is the blue line, and it stays consistent at 15. It would just be the 15 minus the green line, which is the distance from the x-axis to the curve, which is given to us by the function, right? So it would be 15 minus the function, and the function in this case is 9 minus x squared. So that would be our large radius. The small radius, right? The small radius is from that axis of rotation to the the curve that is closest to the axis of rotation. Well, we need to find it in a similar fashion. If we went from the axis of rotation to the x-axis, that would be 15. And then from the x-axis to that curve is consistently 12. It's the function, but this function is just y equals 12, right? It's the function y equals 12. So we would once again take the 15 and subtract the function, which in this case is 12. So if I simplified these, my large radius, I would distribute this negative. It would become 15 minus 9, which is 6, and then plus x squared, while my small radius would just be 15 minus 12, which is 3. Okay, and now I could use those in order to plug in to my generalized formula for the washer method, right? So it would be pi times the integral from a to b, and in this problem we were told to go from 0 to 3, so it's from 0 to 3 of my large radius, which is 6 plus x squared, so my large radius squared minus my small radius squared, and my small radius is 3, so 3 squared. And then we have a horizontal axis of rotation. So we are going to take the integral with respect to x. And that right there is, once again, something that could be put in your calculator. But I just wanted to make sure that I showed you how to set those up whenever the location of the axis of rotation changes. It may not always be the x-axis. It can move up and down. And when it does, you just have to do a little extra work to find out what your radius is going to be. And from there, the problem works the same.